Alright, welcome back, and in this video we are going to look specifically at linear and quadratic functions. So to start with, we're going to look at a refresher linear function. So function essentially is a grown-up way of talking about an equation. In this case, instead of saying y equals, you'll notice that you usually have some variable of x. So if you look at this example, it says h of x. Essentially, it is talking about inputs and outputs in a little bit of a different way, but the way you approach solving the problem is very similar that you would approach it if it was just a straight linear equation. Now in this particular example, we are looking specifically at graphing the function and how that works. And in order to do that, the easiest thing to do is to find your x and y intercepts and to find your slope. Now the other way that you could do it is you could use slope and the y-intercept. It is totally personal preference how you want to go about it. But you do need to use at least one method in order to graph. So first, in looking at this example here, notice that it is a fraction, and so the first thing you'd want to do is get rid of that fraction. You do that by multiplying your entire equation by that denominator. Since I only have the one fraction, I only need to worry about the 1. However, we cannot forget that I've got this negative here. So this negative is actually applied to both of the pieces on top, and this is how that works. So multiplying everything by 2 turns this kind of into, say, 2y is equal to a 3x minus, and now you need to open a parentheses because this becomes 2 plus the 6x because we haven't distributed it yet. Once you do that, we need to take this negative and we need to distribute it through this parenthesis here. So this becomes 2y is equal to 3x minus 2 minus a 6x. I need to combine my like terms here. So this gives me a 2y is equal to and this should have been a 6 here. So my x's are going to completely go away, leaving me with a negative 2. And then divide everything by the 2, and we end up with y is equal to negative 1. Once we do that, this right here is the actual equation of the line that we are working with. So there's a couple things to notice here. First, if I try to identify a slope, my slope here is 0. Okay? Why? Because I don't have any x variables. Now, the other thing to notice is that if I want to identify my y-intercept, I have the point 0, negative 1. Now, this also means identifying an x-intercept is going to be none. In looking at all of this, what this tells us is that we have a special case line. So I would go ahead and I would graph my point. So I'm going to be here at the point 0, negative 1. So this is right here. And then I don't have a slope. My slope is 0. So that means that my line is not going to change my y values at all. So I have a special case. The special case here that I have is one of horizontal lines. Now, what's important to note about horizontal lines is that they are always y equals a number, or y equals a constant. The other thing about them is that they always have a slope of 0. Okay, So those are some things that you need to keep in mind when talking about or thinking about a horizontal line. Now getting into quadratics is going to be a little bit different because there's a little bit more to working with the quadratic function. First and foremost, we have to remember that quadratics are parabolas. Parabolas are the U shape. They either point up towards the sky or they point, say, down towards the ground. I like to think of it as they either smile at you or they frown at you. There are two different forms of quadratics that you may have. The first is called transformation and or translation form, and that is the form right here, where we have new variables h, k, and a. What's important about this transformation form is that it gives you everything you need. What I mean by that is the only things that we care about the most is going to be h and k. H and k are going to tell us the vertex. So your vertex is the coordinate point hk. It gives you that axis of symmetry, which occurs at the h value. It also gives you your max or min value, which all again occurs at the k value. We also get the domain and range. So the range are your y values. The domain is generally going to be all real numbers. And then we have two kind of rules. If your a value is positive, then your range is going to have the form k to positive infinity. If your a value is negative, then your range goes from negative infinity to k. Basically, if your a is greater than 0, then you are going to open up. And if your a is less than 0, you are going to open down. Now we can also write intervals of increasing and decreasing. Again, if your a value is positive, then your intervals look like so, where you're going to decrease from infinity, negative infinity to h, and you're going to increase from h to infinity. It's vice versa if we have a negative value. Okay. Now, the other form that we have is standard form. Standard form is that good old-fashioned form that we all love to hate, ax squared plus bx plus c. In this form, you cannot actually identify a vertex. So instead, you have to use what's called the vertex formula. The vertex formula is this formula down here, where in order to find h and k, you have to use negative b over 2a, and then you have to evaluate at whatever you found. Okay. So we're going to look at a couple examples so you can kind of see how this works. So first and foremost, we need to identify the following information and graph the quadratic. So all the information that we need to identify is listed here, and then you're given an equation. The first thing that you have to do is you need to identify what type of equation you have been given. In this case, we have been given transformation form. What that means is that I can identify everything I need directly out of my equation. So first and foremost, I have an h value. So here my h is going to be 3. And I have a k value, which is going to be 1. Once I identified those pieces of information, the only other thing I have to look at is what was my sign of the a term. And in this case, I want to note that my a is less than 0. So with that, we can start identifying. First and foremost, I need to identify my vertex. My vertex is found by listing the coordinate hk. Well, I found my h to be 3 and my k to be 1. Now I know some of you may be thinking, hold up, wait a second. Within that parentheses there, the 3 was negative, and thus I made a mistake. I didn't. When we're identifying the h value out of your parenthesis here, it's actually the opposite of what you see. So because my parenthesis was a negative, x minus c dictates that h was positive. If this was a plus, then my h would be negative. Okay, so keep that in mind as you're working your problems. Now with that, I also have the axis of symmetry. And the axis of symmetry was found by looking at x equals h. So in this case, h is 3. So my axis of symmetry is going to be x equals 3. I also need to find my max or min. And so in order to do that, it says first I need to identify it. So here I've got my k value, and I noted that my a was less than 0. This means that we are going to open down. Opening down essentially means that we are going to look kind of like a frown, which says that I have a max value, and it's going to occur at k equaling 1. I also need to identify my increase and decrease. So when I'm talking about increasing, I'm talking about starting at the most negative infinity side of my x, taking a walk along that x-axis, and looking at where you increase or decrease. So here, again, because a was less than 0, it says my increase is going to start at negative infinity, and it's going to travel up to my h value, which is 3. And then I'm going to decrease. So I'm going to start at that 3, and I'm going to travel on down to the positive infinity. Last but not least, I've got my range, and I've got my domain. So when I'm talking about my range, we're talking about where along the y-axis are we going. So because we have a negative value, it means we're going to start at negative infinity and travel up to that k value, which was 1. And in this case, my domain is going to be all real numbers. Now, the other way that we like to write domain is we can say negative infinity to positive infinity. Okay, so either one of those would work as a designation. Now, the last thing that I would consider doing is I would consider looking for your intercepts, because that is going to help you with being able to graph your graph correctly. So your intercepts here, we know in order to find it, says that y is going to be 0, and then I have the equation negative x minus 3 squared plus 1. So the first thing that I have to do is I have to be able to solve. So here, what I would do is I would kind of work my way backwards. I would take this 1 and I would move it over. So to do that says that I have to subtract. So this becomes a negative 1 is equal to negative x minus 3 squared. Divide everything by the negative, so we have 1 equals my x minus 3 squared. Using the square root rule, we can take the square root of both sides, so this becomes plus or minus 1 is equal to x minus 3. I need to take this 3 and move it over, so this becomes that x is equal to 3 plus or minus 1. And now we simply need to finish the math. So I'm going to get that x equals 3 plus 1, in other words, equals 4. And I have that x is equal to 3 minus 1, which equals 2. Now notice these are not actually intercept points, so we would write our x-intercepts as 4, 0 and 2, 0. Now about the only other thing that we could do is we could write your y-intercept value. So when we're talking about your y-intercept, we are talking about x being 0, so here this would be y equals negative of 0 minus 3 squared plus 1. So 0 minus 3 is negative 3, squared is 9. Apply the negative is negative 9, plus 1 gives you a negative 8. So your y-intercept is going to be at the point 0, negative 8. And now we can start graphing. Okay, so we've identified all the pieces and now we need to graph. Start with your vertex. My vertex here is at the point 3, 1. So I'm going to go ahead and go over 1, 2, 3 and go up 1. You need to drop in your axis of symmetry line. So to drop it in just essentially says that you are going to draw a dotted line that cuts straight through your vertex and is a vertical line. Once you do that, the other thing that I would do is I would graph my x and y, or my x-intercepts for sure. So I know that I have the point 4, 0, so that one goes here, and I have the point 2, 0. And the only other point that I have way down here at the bottom is I've got this y-intercept, and in this graph I can go ahead and do it, so that would cross right about here, which also means I could go to right about here. Once you have your points, you just simply kind of connect your dots to the best of your ability, make it as close as you possibly can. And there's your quadratic. Alright, now what happens if instead of transformation form we are given standard form? Well, standard form says that we have to start by using the vertex formula. So we have to remember h is equal to negative b over 2a, and k is equal to my function evaluated at the h term. So I need to identify my a, b, and c. So remember, standard form is ax squared plus bx plus c. So in this case I care about b and a. So when I'm looking for that h value, I have negative b, so negative of negative 1, all over 2 times a, so 2 times 1. In this case, negative and negative is positive, so we end up with an h term of 1/2. Once we do that, we need to evaluate by it. So in order to find my k, says I have to evaluate my function. So here, my k is going to be found by taking my 1/2, square it, minus my 1/2, minus 6. So in working that, you should come out with negative 25 over 4 as being your result. So please take a moment and actually do the math here and make sure you come up with what I got. So this now allows you to start. So first we had to find that vertex, which is at the point 1/2, negative 25 over 4. This allows us to list that axis of symmetry, which we found to be x equals 1/2. It also allows us to state what we have, and so in this case, if we look at this a term, we need to note that a is greater than 0. This means we are going to open up, and opening up simply means that we're going to have a smiley face here. So this means we are going to have a min value at k equaling negative 25 over 4. We can also do increase and decrease. So in this case, we're going to have our decrease is going to go from negative infinity to 1/2, and our increase is going to go from 1/2 to the positive infinity. We know our domain is going to be all real numbers, and we know the range is going to go from our value up to positive infinity. So the only thing that's missing is being able to solve for my x-intercepts. So my x-intercepts are found by solving the quadratic. So I have 0 is equal to x squared minus x minus 6. In this case, we can factor this pretty easily. Break this into x and x. Factors of 6 that are going to give me a negative 1. So in this case, we're going to have a negative 3 and a plus 2. So we need to be able to solve this. So here we're going to end up with x equals 3 and x equals negative 2. Again, we need to write them as actual points. So this becomes the point 3, 0 and negative 2, 0. Again, we need to just simply graph what it is we know. So graph your vertex. So here we have 1/2 and 25 over 4. So 25 over 4 is roughly 6 1/4. So here we're going to go over 1/2, and we're going to go down a little more than 6. So kind of guesstimate right there. We can drop in that axis of symmetry line, so it's going to kind of go right here. Next, we can graph those x-axis points. So we have 3, 0. So here we go 1, 2, 3. And then we've got negative 2, 0. So right here. And then we just simply connect our dots to the best that we can. And there you have it. So whether you start from transformation form or you start from standard form, the approach is going to be similar. Just remember, if you start from standard form, you have to use that vertex formula first. So the vertex formula again says that you are going to find h by doing negative b over 2a, and then you find k by evaluating your function at whatever you calculated h to be. Now the last thing that we need to look at is a couple of application problems. So here I have that Cindy wants to construct 3 rectangular dog training arenas side by side using a total of 400 feet of fencing. So first and foremost, I would draw what you have. So we have a giant rectangle that has been cut into 3 pieces, or slides of fencing. We also know about this rectangle that my total fencing is going to be 400 feet. We also know that this distance here is your length. We know this distance here to be the width. So in general, this is what we have. What that also means is that this length, this length, this length, and this length are all the same. Okay. It says, what should the overall length and width be in order to maximize the area of the 3 combined arenas? Let x represent the width. So there's a couple things that we need to remember about this. First, we need to remember that when we're talking about perimeter, we are talking about twice the length plus twice the width. Also, when we are talking about maximum area, we are talking about the idea of length times width. So first and foremost, we need to look at what we have. And so we're going to let x represent that width here. We know your total perimeter is going to be 400. So I have 400 is equal to twice the length plus twice the width. Okay. I can pull a 2 out. So in this case, what we actually have to do is start it this way. When we're looking at, we've got 3 rectangles here. So if we're actually looking at what we have 4 individual widths. So we're going to start with the idea that we have 400 feet of fencing. We've only got 2 lengths, 2 long sides, but in this case we have 4 of your widths, and the widths are x. Okay. So here, when we do that, the first thing we can do is we can still pull out that 2 I was talking about. So here, if we pull out the 2, we've got length plus 2x left over. I can divide that 2 completely away, makes this 200 is equal to the length plus the 2x. I want to go ahead and make this in terms of length because I have to be able to find area, and we need to try and get rid of one of the variables. So I'm going to go ahead and solve this, which means my length is going to end up being 200 minus the 2x. Okay. So I'm going to use this idea right here in order to find my area. So when I'm looking at the max area, I need to plug in what I know. Well, first of all, I know max area is found by doing length times width. So in this case, my length is going to be 200 minus 2x, and my width is going to be x. I need to distribute this x through my parentheses, so this becomes 200x minus 2x squared. In working with this, I now have an equation. So with this equation, I can actually use your vertex formula to find your max width. So here, what we're going to do is we're going to use that idea that h is equal to negative b over 2a. So here I have my formula. So my max area is a negative 2x squared plus my 200x. So notice what I did was I just simply rearranged my equation so that I could pull out the proper a and b. So in finding my vertex, what's going to happen here is I'm going to find my h to be negative b, so negative 200, all over 2 times a negative 2. When you do that, we end up coming out with 50. So what this means is that I have now found my max width to be 50 feet of fencing. The only other thing that's left is to calculate that max length, and so to do that just simply says I need to plug in for my missing value. So to find that max length, I'm going to solve 200 minus 2 times my 50. In doing so, I come out with 100, and this would be feet. So my overall dimensions for each area is 50 by your 100. So here we've got that max width at 50 feet, and we've got the max length at 100 feet. So when we're looking at your little drawing, it means this length right here is going to be 100, each of these is going to be 50, and then this back piece again is going to be 100. The last problem I wanted to look at is a velocity problem. It says a ball is thrown upwards with a velocity 48 feet per second from the top of a 144-foot building. The height of the stone t seconds after it has been thrown is given by the following function. You need to determine the time at which the stone reaches the maximum height and find the maximum height. So if we look at an image of what we're doing, we've got this building here. We are standing up on the top and we are tossing a ball off. Okay, so that's essentially what is happening. So this distance from here down to the ground is going to be 144 feet. And then we're throwing with an initial velocity. So my velocity is going to be 48 feet per second. And we want to know how many seconds it takes. So here we have to simply plug things in. So I've got this h of t is going to be negative 16 t squared plus my initial velocity of 48 t plus my initial height of 144. In this case, we can use that vertex formula. So in order to find my time, this would be like my h value. So we are going to use negative b over 2a. So in this case, we've got negative 48 all over 2 times negative 16. So my time is going to come out to being roughly 1.5 seconds. Now, in order to find your maximum height, that is going to be like your k value. So in this case, what that means is that I have to plug in my time in for t. So to find it, says I'm going to take this negative 16 times 1.5 squared plus my 48 times 1.5 plus the 144. And so when you do all of that, we come out with roughly 180 feet. Now, why does this actually work? Well, if we were to look at a graph, one thing that we know is that my time would be your x value, and then your maximum height is that k value. So when we throw anything, we always start at 0. It's going to go up for a little bit of time before it peaks, and then it comes back down to land. So this point right here up at the top is your vertex point. And so therefore, because it's your vertex, we can use that vertex formula idea in order to solve the problem. So if you have any questions, please let me know. Otherwise, I will see you next time.